In many situations that occur in ecology, biology, economics, social sciences, a quantity changes at a rate proportional to the amount present. In such cases, the amount present in time t is a special function of t called the exponential growth or decay function. Let y sub 0 be the amount or number present at time t equals 0. Then under certain conditions, the amount present at any time t is modeled by y equals y sub 0 e to the kt, where k is a constant. You might notice that this looks fairly similar to a equals p to the e rt. K is essentially our rate then. Principle, what we start with, the amount we end up with. What we start with, what we end up with. If k is positive, the function describes growth. Examples of exponential growth are compound interest, we've already done, atmospheric carbon dioxide. Where k is negative, the function describes decay. One example of exponential decay is radioactivity. The growth of atmospheric carbon dioxide over time is recorded in this table. Now we can see how to determine such a function from the data. So we're going to make an equation of the form y equals y sub 0 e to the kt from this data. Find an exponential function that describes this amount from the data. Well, let's go back, and year 1990 is 353, and year 2275 is estimated to be at 2,000 parts per million of carbon dioxide. So going with that, we have, just record so I don't forget, 1990 was 353, and the 2000 happened in the year 2275 is when that's estimated. This is going to be year 0, time equals 0 there. And this one, time is 285 years later, from 1990 to 2275. So starting the equation, the later amount is 2,000 equals my original amount with time 0 at 353. That'll be e to the kt, and k is what we're needing to find right now. T is 285. We're needing to find k. So first thing we'll do, we'll divide by 353. So 2,000 divided by 353 equals e to the 285k. We'll take logs of both sides. So ln of 2,000 equal over divided by 353 equals the ln of e to the 285k, which we know is just 285k. Now k will be the ln of 2,000 divided by 353, and that whole thing divided by 285. So k turns out to be, the value we're going to use, approximately 0.00609. So my equation turns out to be y equals my amount in year 0 of 353 e to the 0.00609 T. And this is the formula then I can use to find the increase in carbon dioxide. And let's use that formula then. So writing it down quickly again so we don't forget. Y equals 353 times e to the point 0.00609 T. We want to estimate the year when future levels of carbon dioxide will double the 1951 level of 280 parts per million. So that would be 560 parts per million. That's what we're aiming for. So 560 equals 353 times e to the point 0.00609 T, and we're solving for T. We'll divide by 353, so 560 divided by 353 equals e to the point 0.00609 T. Now we'll take the natural logs of each side. So ln of 560 over 353 equals 0.00609 T, or T will equal ln of 560 divided by 353 all over 0.00609. And when I grab my calculator, that comes out to approximately 75.77, or I can add that onto my 1990, and I find that that is 2065.77. So during the year 2065, the carbon dioxide in parts per million is estimated to double the amount we had in 1951. So that would be my solution.